ACDH Tool Gallery, Generative Artificial Intelligence and Vibe Coding. Chapter 4, Vibe Coding Tips. On the following slides, I will first give you some more background on vibe coding and some basics of software development. After that, I will share practical tips from my own work as a low coder using the coding assistants Claude Code and OpenAI Codex, both primarily as CLI tools. Vibe coding, a term coined by Andrei Karpathy, refers to intuitive, dialogue-based programming in natural language. Vibe stands for flow, feeling, and creativity. This makes it possible to produce results quickly from a script to a small app. For CLI assistants like Claude Code or Codex, you should have a basic understanding of software and infrastructure. Pure no-coders are better served by apps such as Claude Desktop or commercial app builders. My core argument on this slide: the humanities are context-driven domain mastery. Vibe coding and prompting depend above all on precise context management. And that is exactly what scholars in the humanities excel at. They formulate things precisely and know their domain in depth, ideal for planning, steering, testing, and evaluating LLM outputs. Why this is ideal for vibe coding in natural language? In 4 points. First, prompting means formulating a precise question, a core skill of our discipline. Second, we work iteratively rather than expecting a one-shot result, just like text revision or source criticism. Third, we abstract and focus on what should be created, not how each line is implemented. And fourth, we think semantically rather than in syntax, and vibe coding rewards meaning, structure, and clarity of purpose. Let me walk you through the vibe coding roadmap. The core idea is simple. Vibe coding lives from structured context and iterative feedback. So everything starts with planning, because to fail to plan is to plan to fail. And do the planning together with the AI. Set explicit goals and constraints, then have the assistant draft a plan and present it to you before it writes a single line. Reviewing that plan up front is the most reliable way to avoid costly wrong turns. It's all about context and context management. The better and more structured the context you provide, the better the output you get back. And here is the central message: precision beats language. Use your preferred natural language, English, German, or whatever your mother tongue is. The language matters far less than your ability to formulate precisely. Precise formulation is the single biggest lever in vibe coding. Treat your AI assistant like a junior dev, capable but in need of guidance. But keep in mind that coding assistants probably know more about software development and infrastructure than you do. So don't treat the AI like a fool. Documentation, usually as markdown files, together with Git versioning is a must. It gives you a history and a backup of your code. Let the AI run multiple tests rather than trusting the first result. Coding assistants are testing experts and know how to do it. You just have to ask them to. And finally, use other LLM counselors for auditing and debugging, a 2LLM or 4 eyes principle. Before we criticize AI, it is worth taking an honest look at classic software development, because there too, accepting black boxes is the standard, not the exception. At its core, development always rests on chains of trust. None of us ever fully checks the compiler, the program that translates our code into machine language, the so-called JIT compilation, which only optimizes code while it is running, or the countless libraries that pull in other people's ready-made code. We trust that they do what they promise. That is not a reproach, it is simply reality, and it works remarkably well. What matters is not how a piece of code came about, but whether I know its assumptions and can test and correct it. Serious development therefore relies on verification, on tests, on types, that is, rules about what kind of data is allowed, on linting, which automatically checks the code for errors and style problems, on runtime checks and observable behavior, not on the origin of the code. And this is exactly where the bridge to AI lies. Whoever can test and judge code understands it operationally, no matter whether it was written by a human, a compiler, or a language model. This slide gives an overview of the landscape of vibe coding tools, and it is more complex than you might first think. Roughly, they can be ordered by their degree of autonomy. The simplest is code completion right inside the development environment, the IDE, short for Integrated Development Environment, the program a developer writes code in. The best-known example is Visual Studio Code, or VS Code. It suggests the next line as you type, ideal for developers who already code anyway. One level up are LLM extensions that add a chat assistant to an existing IDE, and agentic IDE forks, that is, complete development environments with a built-in agent that plans and executes on its own, aimed at developers and ambitious low-coders. Then there is the terminal world, intelligent terminals that offer AI commands, and above all, the CLI agent tools, standalone command-line agents that take on complex tasks. These are the most powerful tools, but they require a basic technical understanding. These are what I use myself as a low-coder. At the other end of the spectrum, and especially interesting for no-coders, are the prompt-to-app builders. They generate runnable apps purely from natural language without any code editing. And finally, the standalone coding apps, which enable development directly through language without a classic IDE. You can look up the specific product examples in the table. My point here is mainly that you understand the categories and who each one is for. This slide gives the background that is often missing. Where does the LLM inside our coding apps actually come from? Most people experience it like power from a wall socket. It's just there. But just as electricity isn't created in the socket but in a power plant, the language model doesn't run inside the app itself. An LLM is essentially a huge program that needs a special runtime, a so-called inference engine, the machinery that actually makes the model compute. And that runs either in the cloud, in a data center, or locally on your own machine, but practically never directly inside the coding app. Let's look at the upper diagram. On the left is the user or the app. It sends the prompt as plain text over the internet, via HTTP. The central element in the middle is the API, the interface through which two programs talk to each other. It handles authentication, that is, who is allowed access, the routing, and rate limiting, which caps the number of requests. Only behind that, on the right, sits the actual data center with the inference engine and the model on a GPU cluster. And that brings us to the GPU question. A CPU has a few, very fast cores and processes tasks step by step, simply too slow for large LLMs. A GPU, by contrast, has thousands of cores that compute in parallel. That is exactly what language models need, because at their core, their computations are huge matrix multiplications, masses of identical operations in parallel. That's why the GPU is the standard for LLM inference, and a plain CPU achieves little here. We just saw that the model itself runs in its own runtime, the inference engine. Now let's look at the other side, the applications on our own machine that talk to that data center. They too are a kind of runtime, but for the communication, not for the inference itself. We provide our text as a prompt in the chat, or images, audio, video, whatever it may be. These apps transfer our input, send the data through the API to be processed in the cloud, and then return the answers to us. And these apps differ. There are general chatbots like ChatGPT that everyone knows. You type text and get answers back. But these systems have no access to your computer, neither to your files nor to the console. That is a fundamental difference. Any code they generate can only be moved into an IDE like Visual Studio Code by copy and paste and run from there. The agent itself has no direct access to the codebase, which is a big drawback. Coding assistants solve this with a so-called harness, an environment that gives the AI the tools a developer actually needs, executing and testing code, accessing the file system, generating project descriptions, working through to-do lists, and so on. Everything a human developer would need is made available in assistants like Claude Code, Codex, or OpenCode, and that is the decisive difference. Now we move from the fundamentals to the practical tips. The first three we've already touched on, so I'll keep them brief. The fourth is new. First, Git and versioning. This is really important. It's your backup and your version history. Setting Git up and understanding the basics takes less than an hour, but it pays off enormously in vibe coding. Every intermediate state is backed up automatically. Every version can be restored. You can use branches for experiments, and you can even have the LLM write your commit messages. Second, the 2LLM principle, our version of the 4 eyes principle. Let a second LLM counselor audit the codebase and watch over the debugging, with both assistants having full access. In practice, that can be, say, Claude Code and Codex running in parallel. Third, test, test, and test again. Keep reminding your coding assistant to test. Have it generate test scripts. Use the LSP, linters, and type checking. Run the tests after every change and feed error messages straight back to the agent. And fourth, the new one, Python environments. Virtual environments are a must. Global library installations lead to version conflicts and pollute your host system. Use a Python venv, or even better, miniconda, and always keep your requirements.txt up to date. That keeps the host clean and your setup reproducible. By now, you've already learned a great deal about generative AI, software development, and vibe coding. I won't explain everything in detail from here on. There isn't room for that, and it isn't really necessary. Just ask the AI assistant of your choice and have it explain things to you. Ask it, for example, to explain Git, how it works, and how to install it in your first project. One tip, a git ignore file is very important right at the start of the setup. And never nest Git repositories inside subfolders. That breaks the system. Your assistant will also explain what Python environments are and how to set up LSP, linters, and type checking for your testing. Trust me, these are exactly the mistakes I made myself at the start. No Git at all, then Git nested in some folders, and of course, no testing. The first tips were about how you work. Now it's about what you should feed the AI assistant with. Good documentation in the right file formats. First, project documentation. Keep 3 files maintained from the start. The PRD, the Product Requirements Document, which describes what the software is supposed to do. The README, with the repo description and changelog, and a to-do file for structured task lists. Second, the most important file, Claude.md or agents.md. This is essentially the operating system of the agent, the file it reads on every start. Here you define programming languages and frameworks, set the testing strategy and team rules, and give style and formatting guidelines. Third, the format, Markdown, that is simple text markup with a few special characters for headings and lists. You can learn it in about half an hour. It consumes few tokens, the amount of text the model has to process, and LLMs read it far better than plain running text. Ideal for PRD, README, and Claude.md. And fourth, XML and JSON for examples, data, and pipelines. XML for clear, flat structures. Please no TEI or deep hierarchies. And JSON for training data and processing chains. The basic rule everywhere, too much markup means high token consumption. And a recent update from Anthropic. While Markdown stays the right choice for what the AI reads, your Claude.md, and specs inside the loop, they now recommend HTML for what you, the human, are meant to read. An HTML view renders in any browser, is far easier to share via a link, and gives much more comfort for complex content like long plans or reports. The trade-off is that HTML consumes more tokens, and as mentioned before, have the AI explain the different formats to you. Your agent knows very well how to handle each of these types. And last but not least, coding assistants can do system administration too. Any assistant with file and system access can reach the shell, bash on Linux or Mac OS, PowerShell on Windows, and actually run things, execute Python programs, test them, and debug right there in the runtime. Claude Code makes this remarkably easy. But And this is the important part. You have to get the permissions right. Giving the assistant system-wide access beyond your codebase is very risky. If you allow it at all, allow read access only. Outside the project folder, never grant write or delete rights. Those read rights do have real benefits. The assistant can read Windows event logs, analyze and explain errors, inspect system configurations, and help diagnose PC problems. That can save you a lot of work. With write or delete access, the same power becomes genuinely dangerous, so configure it carefully. So here's the recommendation for vibe coding. Minimal rights, maximum safety. Give full access only to the project folder. Outside of it, read access at most, and no global write or delete rights. For risky experiments, use a sandbox, Docker or WSL2 for example. And here is my favorite image to close with. And the best part is, this is not fiction. It actually happened on my machine. I was controlling Claude Code remotely while I was out. Only when I got back did I see the blue screen. Windows had crashed and could not be rescued from the keyboard anymore. Critical process died. But Claude Code was still alive inside WSL2. And from there, it was able to diagnose and fix the problem. That is Claude Code as Jonah in the whale, trapped in the Windows crash, alive in WSL2. 2 lessons from this. First, these assistants can do far more than write code. This was real system recovery. And second, a sobering security point. Software isolation through WSL2 is nice, but an agent with bash access can, on request, cross those soft boundaries without much trouble. With an LLM in the loop, the only truly effective sandbox is probably a hardware barrier.